All right, this is one more tutorial on torque, and in particular, this talks about balancing objects across a fulcrum. All right, here we're wanting to balance a 3 Newton weight against a 5 Newton weight on a beam. So this didn't quite print extremely well. So our 5 Newton weight is over here, and it's pushing down with a force. It is 20 centimeters from the fulcrum, which is right here. And so where do we need to put this 3 Newton force over here to balance out the weight is really what we're asking. So to get that, we're going to say, what is the torque on the 5 Newton weight only? So what's the force? 5 newtons, and it's 20 centimeters away. Now, which way is it going to rotate? It's going to force it to rotate clockwise if it were to continue to rotate and not hit the table or whatever here. So since it's rotating clockwise, we're going to give that a negative sign. So negative 5 newtons times 0.2 meters is 1 Newton meter. Now to figure out where to place the 3 Newton weight, I just need to set that equal to the 1 Newton meter. So B, the torque for that 3 Newton weight, essentially going to be 3 newtons times L, which I don't know, is going to be equal to 1 Newton meter, because the torque's got to be the same if it's going to balance, but it's going to be positive because it's got to go the other way. So my L is going to be 1 Newton meter divided by 3 newtons. Newtons are going to cancel, so we get 0.33 meters or 33 centimeters. And so that's about where we would place the 3 Newton weight. This other one, we have a boy walking out on a dock. He's walking the plank, so to say, and he's getting out past where this is going to tip. This length is 1 meter long. The plank from the end to where it meets the end of the plank is 3 meters long, so you got a 4 meter total plank. And we're going to treat the edge of the dock as the fulcrum point. So we've got an 80 Newton plank as shown. The plank is uniform density, so the center of the gravity plank is located in the center of the plank. So that means we'd come at this 2 meter spot, and that is where the weight is coming down. So we're going to assume that that's an 80 Newton plank, and we're 1 meter from the fulcrum spot, or at the 2 meter spot from either direction on the end of the plank. So now what's the weight of the plank? And we want to know that torque. So the part A, the torque is force times the length of the lever arm from the fulcrum point, not the end of the plank. And so it's going to be 80 newtons, acting from the center of mass, which is 1 meter from the end. That would want to produce a counterclockwise rotation, so it's positive. And so it's going to be 80 Newton meters. Now, how far can the 150 Newton boy walk out? Less than a meter, but let's figure that out. So we've got the force times the length of the lever arm. So 150 newtons times the length of the lever arm is going to equal 80 Newton meters. So then the length of the lever arm is going to be 80 Newton meters divided by 150 newtons. Newtons will cancel. 80 divided by 150 is 0.53 meters or 53 centimeters if you prefer. Any farther than that, it's going to tip. That's when it's on the verge of tipping, so the weight and the torque are just evenly balanced. Any more than that, it's going to tip over. All right, so this has been a tutorial on balancing torque.